Good afternoon, everyone. So our first session is Associate Professor Phil Teakle. So to give a brief introduction about him, his fascination with rocketry led him to filament winding. Oh, that's interesting. And he found the Teakle Composites in 2008. And now Phil is our expert at UniSQ. He's the expert in filament winding since 2024. So I'll let you share the screen and you can start the presentation.
Okay, just bear with me. Now, can you see my presentation? Or have I shared the wrong screen?
No, you can just do the presentation mode. It's still on the slides.
Okay, if I click on that one, slideshow.
Yep.
That's correct. Okay. All right, that's you can see the title slide. Okay. All right, I'll get started then. So I'm using this presentation as an opportunity to introduce myself a little bit and also to give a high-level discussion of the filament winding capability that we have at the University of Southern Queensland. So just the very few essential facts about myself. I started in my current role in almost a year ago now, so not quite. So I'm fairly recent, and I'm aware that I haven't met very many of the people in CFM, especially many of the people working at Springfield campus, but also quite a few at Toowoomba. As Sashini said, I've had a lifelong fascination with rocketry, and that has been a sort of the driving force that's led me to do a lot of the things that I've done in my career to date, including filament winding, which hopefully will become apparent in the next few minutes. I'm trained as a mechanical engineer. I did my undergraduate degree and master's degree at the University of Queensland. Then I did some work in industry and came back and did a PhD at QUT as a sort of mature age student. That was about 20 years ago. After that, I worked at CSIRO for a time, and I then left that to found a company that was designing and manufacturing mainly filament wound items. So the company, that brings a bit of a different perspective to when I was working at CSIRO, and hopefully something that will be useful in my current role here. So first of all, what is filament winding? I assume some people know quite a lot about it, but there might be people who don't know much about it at all. It's a manufacturing technique, and as the slide says, resin impregnated fibers drawn onto a rotating mandrel, and the fibers are accurately wrapped in a pre-calculated pattern. And if I click on this button, you can see the process in action. That's just a small mold looking a bit like what a tank or pressure vessel might look like, and that's carbon fiber being wrapped over it. And that first layer wrapped sort of lengthways, that's called a helical layer often, and this layer that's being wrapped currently, we normally would call it a hoop layer. And the fibers can be placed to according to the stresses, the predicted stresses in the part. So it's a very efficient manufacturing technique. You can see it's quite rapid as well. And you can see by the regularity of the patterns that it can be very accurate, and especially with the great machine that we've got in P11, that's a very precise, very capable machine. So why filament winding? Why not other aspects of engineering? I guess, again, it comes back to that fascination with rocketry. I had the ability back in year 2000 to manufacture solid rocket propellant, and I needed to burn it in something. I needed to make a rocket motor, really. The first one we made, you can sort of see on the right side of the screen, that was a very heavy steel motor, and that was fabricated at the University of Queensland workshop. It would have been, reasonably expensive to make. But it was very heavy, and it was reusable. But I wanted to make lighter weight rockets, things that might conceivably fly pretty well. But this was largely a hobby for me, even though I was working a bit with students at the University of Queensland. We had a very small budget, only hundreds of dollars, and I needed a way to make casings. And I recalled reading at high school about these filament wound casings, which were back in the 80s, they were the latest, most advanced technology for solid propellant rockets. Back then I really didn't think much of it, because I thought, how can you possibly make something that holds pressure out of filaments and fibers? But in desperation, really, I thought, well, I can probably afford fiberglass, and I can afford some epoxy resin, and now I just need a means to put them together and make cases. And of course, that took a long time, but I had more time than money back then. And I started working out how to calculate fiber paths from first principles and writing programs to do that. And I had the help of friends to help make a machine to put the fibers in position. And the picture in the bottom of the slide there, that shows one of our very first attempts at making a casing. And you can see that it really looks pretty good. And I think the satisfying nature of filament winding, of having these quite attractive, regular geometric patterns, really appeals to me. And that spurred me to keep on going and developing the technology further. And some of the casings we made, we wrapped them over propellant, and we did test fire them. It was all done legitimately. We were licensed to do these activities, and these tests were done at various government sites. And the casings performed very well. We did have some mishaps, but that was not really due to the casing manufacturer. That was for other reasons. But these are some clips. And but then there was a bit of a turning point where I guess I was reviewing an article or doing some reading on filament winding, and I came across this chart, and it shows the stiffness to weight ratio and strength to weight ratio of pressure vessels made with various materials. And I noticed that the composites, dramatically outperformed even fairly advanced metallic alloys. And the start of an idea occurred to me that the filament winding capability that we were developing was possibly something that could be quite valuable, not so much more than the rocket motors, which back in those days there was hardly any demand for. There was not the public acceptance and public fascination with space, really, that there is now. So back then you were still seen as a bit of a nerd if you were into rockets and space. It's much more mainstream nowadays, and much more encouraged, I would say. But it occurred to me that there might be other applications for this filament winding capability outside of rocket motors and casings. One of the interesting things about filament winding is that you can combine the shape of the part that you're wrapping with the properties of the material and the winding pattern to get what you call an optimized structure. So theoretically, every filament and every length of that filament, or along every length of each filament, it's subjected to the same stress. So you're getting 100% material utilization. There's no material being wasted. That combined with extraordinary high strength of the reinforcement fibers, glass has got a tensile strength typically around 2.5 gigapascals, which is much higher than most metals, and carbon fiber is about double that. And also their low density, you can end up with these extremely lightweight parts, and that opens up a lot of possibilities where weight is critical. But there are also other desirable properties, and this isn't really unique to filament wound parts. This is really to do with almost any composite material. They tend to be corrosion resistant. In manufacturing, you can embed sensors or wires or optic fibers, that sort of thing. So you can really enhance the functionality of the material in a way that you can't so easily with, say, metals. And in the area where I was working, it was important that it was also transparent to various types of radiation, which I'll touch on a little bit later. There are the usual challenges with composites. They need to be protected from point loads and impact. Recyclability is a real challenge for most composite materials. The temperature, the range of operating temperatures is more limited compared to many metallic materials, although we're working on that and more on that later. And in terms of filament winding, some geometries are a bit tricky to wind, especially where you've got concave surfaces and where the fibers want to bridge over concavities, or there are steps. They're not impossible. Anything is really doable, but it just takes a little bit more effort to make that happen. So some of the applications I worked on, there are many, but just a small selection that I worked on before, or as Teakle Composites, and even a little bit before Teakle Composites was founded. Well, I shouldn't start at the top. We really started with the bottom one, hypersonic nose cones, which is a bit of an odd place to start. We were, or me and some friends, colleagues that I was working with, including Fabian Zander, who's a staff member in CFM or at UniSQ. He and I were, we knew the high fire or high shot people who were making scramjets and testing them. And I remember getting a call and they said, look, our scramjet's getting too heavy. We need to save weight somewhere. Can you make us a lightweight nose cone? And so that image of the rocket horizontally, that's actually quite a large rocket. The nose cone, which is circled, that's about 2 meters long and then 600 millimeters diameter. And that was one of the first things that I manufactured and effectively sold to someone else. And that probably was a bit instrumental in my opting to leave Cyro and start my own business. That it did launch. It got to Mach 9 or 10, I think, and the nose cone worked fine, which was a great relief. We also made high subsonic aircraft instrument pods for BAE Systems. That was a very challenging application, but we were successful and we got quite a few repeat orders for those pods. Downhole instrument housings, we had the challenge of joining composite materials to metal ends, but this is where the radiation transparency of materials was important. They put instruments down boreholes and they can use electromagnetic radiation or other gamma radiation or other rays to irradiate the material around the borehole, and they can detect from the return signals, what the composition of the material is, and also what the structure of the ground around the borehole is. And that's difficult to do with steel rods, which are relatively opaque to those sort of that radiation. But our bread and butter, and this happened some years after I started Teakle Composites, I got contacted by an engineer from a coal seam gas company who said that they're not allowed to line their long horizontal boreholes with steel tubing, and they wanted to try other materials, and they wanted a sample of fiberglass tube to evaluate it. And I was used to being asked for samples all the time, and I said, "Oh, what dimensions?" And he said, "Oh, it's about 90 millimeters outside diameter." And he needs 6,000 meters of it for one trial, another 6,000 for another trial, and then if it's successful, they'll need lots of it. And that was a game-changing query. I fibbed a bit and said, "Oh yes, we can do it," and I'll get them a quote. I had one machine that could make 2.5 meter lengths, and when they accepted the quote, we very rapidly had to scale up. But we did that, and that became the mainstay of our business for another 10 years or so. And it was really good, a good engineering challenge too. We were always making improvements and finding ways to make it better. So a little bit more about filament winding itself. There are the materials you can use can be pre-impregnated, so they call it toe preg because the ribbons of fibre are often called toes, and if they're pre-impregnated, you call that a toe preg. It's a very clean way of manufacturing parts because you've already got the fibre and resin combined by the supplier. A lot of the burden of quality control is on the supplier too. They can certify that the resin is properly mixed and in the proper ratios and has the proper fibre volume fraction. So that makes the filament winder's job a lot easier. However, you do pay for that convenience. It is fairly expensive, and you're limited to what the suppliers will offer. So there's not a lot of flexibility there. If you're interested in trying new materials, that's a bit of a disadvantage. What I did mostly, and the machine in P11 can operate in either mode, so it can operate with pre-preg materials, but we can also do wet winding, and that's where you, at the filament winder, you combine the fibre and the resin. So obviously there's a wider choice of reinforcement and matrix that you can put together to evaluate. You've got a bit of control over the fibre volume fraction. It tends to be a less expensive method of manufacturing. However, you pay for that a bit because it is quite messy, and to keep the work area clean and spotless, which we have to do for the facility in P11, there's a lot of protection of surfaces, and then there's a quite elaborate cleanup after each trial. Something that's coming, hopefully later this year, is changing the machine or adapting the machine from just filament winding to automated fibre placement. I thought I'd better mention this. So automated fibre placement is where the machine, well, as the text says, precisely lays narrow pre-impregnated composite toes onto complex 3D molds. It uses heat and compaction as the toes are being laid down to consolidate it. And you can place material in any orientation, in any location. So you've got great flexibility for manufacturing. It's free of many of the constraints that filament winding has. In fact, filament winding can be seen as a subset of automated fibre placement. So that'll be an interesting capability, and I guess when we get the machine adapted, there'll be another presentation on that, describing it in more detail to you. Winding pattern generation, this is a very important part of the activity. So parts can broadly be classified into axisymmetric parts. So that's like tubes or cones or things like that. And that's or pressure vessels. So there are many parts that are filament wound that are axisymmetric. Well, definitely the majority of parts tend to be axisymmetric. And for winding pattern generation, we have two methods. There's commercial software which we have access to called ComposiCAD. It is quite it's a well-written application, user-friendly. It's extensively proven, with other case studies, so that its results are accurate. It's quite reliable in generating useful output. However, it can only handle the most common cases. So it can handle a wide variety of applications, but often in a research environment, you've got people wanting to do something a bit new or a bit different. And that's where any of the commercial packages fall down, because they're a bit limited in their capability. But fortunately, my software being written from first principles, with adaptation, it can calculate almost whatever is physically possible to be filament wound. So we have used that on a number of occasions where we've had tricky problems to work on. However, at this stage, it's not user-friendly. Really, only I can use it. And as time goes by, I'm aiming to port it to some open source language like Python, and hopefully it can be made available for other people to work on. But it does require a lot of investment of time to be able to use software like that. So it's only for the diehards. So yeah, the images show some filament winding patterns, and the upper one is a ComposiCAD output. The lower ones are output and a comparison with the real world winding using my software. Once you've got a pattern, it's then relatively straightforward to convert that to machine instructions that's required to lay down fibers in that pattern. Also, once you've got the pattern, you can then use that information in analysis packages like ANSYS, or doing finite element analysis to estimate the behavior of the parts, and you can build the parts and then do a comparison. Looking at more general cases, so non-axisymmetric parts, that can be done. Presently, the approach we take is to make it a bit like an equivalent axisymmetric part and then follow the normal procedure. But I've been working on a way of doing it more faithfully. So representing the geometry in STL format, which uses triangles or facets, and writing a program to calculate stable paths over that geometry. But you get all sorts of unusual behavior, and it could be quite an interesting and fruitful bit of work to do that. But there would be a challenge in finding a way to come up with useful output where you've got layers being wrapped over parts that don't have voids or openings in them. Yeah, it's definitely a much more tough job. So if people have been in P11, especially on a Monday or a Tuesday, they might have seen the machine being used. And I've just got some clips here of some of the things that we've done. This was just something I did to familiarize myself with the machine and make sure that my software could talk to the machine or generate instructions accurately for the machine. So I 3D printed mandrel that looks like a pressure vessel or looks like a rocket motor casing. And I just used some dry fiber to really demonstrate the principle. There are gaps between the toes, which there wouldn't be in a real filament winding, but that's to conserve material. The process, or the video, has been sped up a couple of times, but when the machine's running flat out, it's not actually much slower than this. I've skipped a few cycles there, and you can see the nice regular helical pattern. And it transitions to a hoop layer. And you might combine intersperse several layers of helical and hoop layers to get a complete laminate. Other activities, we've been evaluating or trialing new materials. So you're probably aware from previous presentations about the work in CFM on oxide composites with oxide fibers and oxide matrices. And we did some trials on the filament winding machine of oxide toe preg. And one of the images is making a unidirectional flat panel, and the other one is winding a tube. And that was to evaluate the ability of the material to be filament wound, and also to look at mechanical properties after the part has been extracted from the mandrel and then cured. Other activities, we have a project with Wagner's currently, and this is for a civil engineering application, making large filament wound poles. And to look at the process, they've made pretty much the largest mandrel that can be used in our facility currently. It's a bit over 3 meters long. It's 400 millimeters in diameter. We can go to a larger diameter than that. But the steel mandrel also weighs 300 and something kilograms. So it's definitely one of the larger parts that I think would be used in the facility. We're using their glass fiber and their resin combination. So that meant using the wet winding process for making specimens of their parts. And I've got a clip of their part being wound. We wrapped, I think it ended up being about 120 kilograms of fiberglass on their mandrel, and trying all sorts of tricky techniques like using pin rings to rapidly turn the fibers around at each end to minimize waste, and also cutting away some excess fibers in the middle of the winding, which is a process that they're considering doing. And you might see the resin bath at the back of the machine with the drum rotating. The drum dips into the pool of resin, picks up a film, and the fibers passing over the drum have that resin sort of pushed and infused into the bundle of fibers. And we have a blade where we can control the thickness of the film, so we can control how much resin gets transferred to the fibers. So this is really just replaying one of the first clips. This is an interesting project looking at low melting point mandrels. Just play the clip again. So the concept is you filament wind a laminate over the mandrel. You heat up the assembly so that the laminate cures, and then you heat it up a bit more, a few more tens of degrees, and the mandrel, which is made out of a low melting point material, melts and runs out of the middle of the laminate, leaving a hollow casing. So that might be of interest for making type 5 pressure vessels, where you want to wrap a pressure vessel and have all of all of the mandrel, no liner left inside, and no part of the mandrel left inside. The other options to make those sorts of things are, quite complex multi-part steel mandrels, or using materials that you cast and then can wash out. So if this is successful, it just adds another option for the designer. And other activities on the machine too. We've had Chris Mimra, postdoc, looking at automated process monitoring and defect detection. So that's kind of automating what we do when we're watching the machine running. We're looking to see if anything's going wrong, and he is developing some techniques, automatic techniques for recording how the part is being manufactured, which can then be used for digital twins and those sorts of concepts. But I'll let Chris talk about that more. So why might any of this be of interest to anyone watching this presentation? Filament winding can allow you to manufacture samples very repeatably, very close to how they're designed. So it's less prone to variation than hand lamination. You can design a part and then have it made just the way you designed it. And so I've reprised those images of the designed part and then the part during winding. And if you look closely, you can see it. The reality is, or the representation is a very faithful representation of the reality of the winding. So it's good for making, if you design a part and you've modeled it, then you want to manufacture one or more specimens for testing. That's definitely something that could be considered. It can also economically manufacture non-woven samples, such as the flat unidirectional panels or tubes. It's also good if you're doing research into pull wound or pull truded products, and you want to try what happens if you change the dimensions or the laminate specification. It can be prohibitively costly to get new dies made up. They're very expensive. So a way of simulating or replicating different pull truded parts is to filament wind them. And I've got a clip of an RHS section being filament wound at my factory many years ago. But yeah, you can vary fiber angles and vary laminate thicknesses, and you can go and test them and get a better idea of how the part is going to behave before you commit to extremely expensive pultrusion tooling. And that concludes my presentation. Thanks for your attention, and welcome any questions. If you don't have any questions now, or if something doesn't occur to you immediately, please feel free to contact me, and I'm always very happy to talk about filament winding with anyone.